computer. This is today's case study we're going to work on. If at least I'll get the glass graphic, I can talk you through what we're trying to do here. Okay, figure 4. Got it. Well, I'll just leave that up. I'll get this tidied up later. You save it. And oh, don't look. That's not, you're not supposed to see this stuff. Stupid blackboard. All right, this is our class. Let me go ahead and quickly throw up a link to today's lesson. Must be 13. Lucky number 13. There's Blackboard reminding me how I'm incompetent. Okay, cool. All right, that should get everything ready. Let's see if there's anybody waiting to check in. Okay, there's not. I have a little bit of a scratchy throat today from all the wind and dust, so I'm not sure I can go the whole time, nor can I speak loud enough. Oh, there is Richard. Don't click on remove. Let him in. So I'll go as long as I can. All right, good evening, everyone, and welcome to lesson 13, ce5362, surface water modeling. And today we're going to start another case study, again of a branch system with a main branch and a tributary. So morphologically, it's quite similar to the last case study. Realistically, it's actually a real location using where practical as much real data as was available. And this is, again, setting us up to get on to higher dimensional modeling schemes. There's nothing particularly new about this example compared to the other one, but it's just another chance to examine our approaches. So if I could actually go to the lesson, and I do not have it rendered yet as a HTML file, so I'll have to go through it this way. So what we're going to look at in this case is a real location. So this is an aerial image of Houston, Texas, downtown. And if you're familiar with Houston, Texas, the main part of downtown is pretty much right under the words plan view. And get this all located. This area right here in the center, where the cursor is circling, that's University of Houston downtown. So if you were in the business of ending higher education in the downtown Houston area, this is what you'd target and make that into a big giant hole in the ground. Ironically, and actually kind of interesting, let me get located here. There's a county jail right there. So if you can't make it to the university, you simply just walk down the street to go to jail. That's sort of funny. This channel up here labeled White Oak Bayou, even though this is clearly an engineered section at this point, actually drains probably several hundred square miles down to this point. And then White Oak Bayou makes a relatively sharp curve right here. And the geniuses that built up this city, when they came there 200-ish years ago, decided this is a good place to build some infrastructure, and then spent the next 200 or so years fighting the erosion that White Oak Bayou was trying to do. White Oak Bayou desperately, my opinion, it kind of wants to go like that and basically cut off this whole lobe of land. That's what I suspect the energy is. And then the other major drainage is Buffalo Bayou, which is this meandering stream right here that it too is forced to make or take a sharp turn. I guess it had an original sharp turn, and it's been sustained by virtue of building a city in the way. And where the two join is a place called Allen's Landing, and it's named after an original real estate developer and hustler, George Allen. Actually, I think George Allen was a comedian. I don't know what the dude's first name was, but there used to be ferries that would sail up Buffalo Bayou from the coast and stop here and let people off, take the cocaine out and ship it back to South America. I'm kidding about that. I have no idea if Houston was ever a cocaine exporting community, but other agricultural products for sure. And this is now a city park. I wish I could zoom in on this aerial image, although there's not much to see, but this is a city park. There used to be Spaghetti Warehouse, I think, right here. I think it's been turned into something else, but that was a good place to go feast and eat way too much food for not very much money, comparably. and then you would stagger down to the opera or the symphony, which is in this area, or the theater. So downtown Houston is kind of was kind of a cool place and still is. Okay, so where the two come together at Allen's Landing is called a confluence, for lack of any other word, very scientific sounding word for where the two streams meet. And complicating this thing geomorphologically is that the average gradient of White Oak Bayou is about twice that of Buffalo Bayou. So you have a comparatively steep stream draining into this relatively shallow stream. And so when a White Oak Bayou is carrying large flow, generally when that's true, Buffalo Bayou will have large flow, but the water entering here, making this turn and impacting onto Buffalo Bayou creates a considerable amount of energy, and it's actually scoured a hole down here. And rumor is there's a railroad engine down in the bottom of Allen's Landing. Now I state that as a rumor because the water, if you were to go visit there right now, well, it'd be dark, so you couldn't see anything. But if it was daylight right now, the water is brown like coffee with a bunch of milk in it. But the scour hole's only about 100 feet deep, so that's within the range of recreational scuba gear. And if anyone was going to go find the choo-choo train engine, they would have by now. So I'll stick with it's a rumor. So anyway, the scour hole has created a problem a while back, and they were afraid they were going to lose the new jail. This was, see, it's 93, so, oh, well, it's going to be almost 93, 2003 is 10, 2013 is 20. It's getting to be almost 30 years. I was involved in a study of this area after talking to the flood control district in the city. They weren't about to let the bayou go straight and do what it wanted to do. So they had this fairly elaborate restructuring or rehabilitation plan along this edge. And the real question hydraulically was, because they were going to change the nature of the stream in this location, was it going to adversely impact Allen's Landing, flood the jail, and so on? Because if you flood a jail, that's actually a bad thing. Unless you have prisoners that you know are getting a death sentence and you put them on the first floor, that's just downright mean. And what they didn't want to do was evacuate the jail every time the water got high. Because every time you evacuate a jail and reload it, you always come up a few prisoners short. So that was the plan. Oh, it looks like we lost Jawad. So I will talk slowly and continue. Okay, so that's the background. Here is a graphical representation of a cross section on Buffalo Bayou, about a mile downstream of Allen's Landing. So somewhere down here. And it has a fairly odd stationing information because welcome back. Jawad, if you're having network difficulties, I understand that, and I will keep talking to the recording. So
Yes, yes, Dr. Clifton. That's why I just switched off my webcam because otherwise your words are getting a bit fluctuated. So that's why.
oh, okay. Well, that's me talking. I'm talking fluctuated. I'll talk slower. But again, if you lose it, don't worry, just reconnect, and this is all being recorded.
Okay, thank you. No problem.
All right. Well, oh yes. So the transect downstream is probably right about here, maybe at location B in this drawing. The stationing information is somewhat odd because when I gathered the data for these transects, I didn't necessarily have them stationed relative to the streamline. So I was using the results of somebody else's work and had to kind of manually, if you will, locate the stationing. So this roughly at station 5,000 feet from some arbitrary datum for this particular channel, we have this shape right here. So this relatively steep wall is pretty much along this bank, because this bank is a reinforced bank in Houston. And then this relatively flat and somewhat slightly depressed part is moving 5,000 feet in that direction. And the transects are oriented so they don't actually cross back into the bayou. So it's weird stationing information. If you just had this raw without an aerial imagery, a person would be challenged to come up with these transects. We have tabular values of survey elevations along these particular transects, and we'll look at them in a little bit. I'm moving to a different part. If we look on Buffalo Bayou, about 1 mile upstream, keep in mind this mental picture. So it comes down steeply. Visually, it looks like a V, and then there's this benching portion. That's where the jogging trail is. And there's been a lot of rehab work since these transects were taken, so they're no longer that accurate. A mile upstream, Buffalo Bayou is, my distance is probably somewhere in here. So there's a transect going across this way. You have a jogging path on the south side of the drawing, and then you have various parts of downtown community on the north side. And the correct spelling of Buffalo is B-U-F-F-A-L-L, not Bualo. That's going to drive me nuts, so I'm just going to fix it right now. Oh, that's cut and paste, can't handle F's next to each other. And then one more Buffalo Bayou downstream, Buffalo Bayou upstream. We'll also look at the tabular. And the last one I got done just before class started was White Oak Bayou upstream. And about a mile upstream on White Oak is up in this area somewhere. And if we look at the cross section, White Oak has this secondary channel up here. So if water were to get above elevation 40 at the location, there'd be flow carried in this overbank portion. There's also a secondary channel here, and there's a bench here, which is the jogging trail. And White Oak has this relatively steep and sized cut, which is the engineered part of the channel. This part here that, again, if we zoomed in, we'd see that that's an engineered cross section. It's not natural anymore. So that is our a background setup. And here's some more information that is not on the server yet, but I'll get it up there. We're told that the bottom elevation just upstream of the confluence is minus 6.71 feet. So up in here, it's minus 6.71 feet. On Buffalo Bayou, minus 9 feet. So right under this bridge is minus 9 feet. And downstream of the confluence, to be about in here, is minus 14 feet. So water coming in from White Oak, while eventually it's going to want to go over this minus 14-foot part, is extremely attracted going from minus 7 to minus 9 feet. So it has a tendency to attempt to push its way upstream of Buffalo Bayou. Now, Buffalo Bayou, while it's slower, is larger and will normally overpower White Oak. So those two streams coming together at this point create an awful lot of energy that destructs on Allen's Landing, which was the original purpose for the study. But for our case, it gives us an interesting case study to practice our modeling skills. The confluence dimensions at low flow are roughly 80 feet in this dimension and 120 feet in that dimension. So roughly 80 feet across Buffalo and 120 feet across White Oak. And the angle between White Oak and Buffalo going downstream is 38 degrees, and White Oak and Buffalo going upstream is 70 degrees. So this angle right here is 70 degrees. This angle is 38 degrees. So even though White Oak is being turned adversely into Buffalo Bayou, it still has generally a downstream angle. If we were using something different than swim, because the angles actually have no consequence in our swim model other than drawing things, those would be important. When we go to higher dimensional simulation, those will help us again construct our computational matrix. Matrix being the diagram, not matrices in rows and columns. The three cross sections have the other information in that the distance from the junction to the Buffalo Bayou upstream cross section is 4,000 feet. So actually less than a mile, 4/5 of a mile, 8/10. Distance from the junction to Buffalo Bayou downstream cross section is also 4,000 some odd feet, again 8/10 of a mile. And the distance from the junction to White Oak Bayou upstream cross section is 6,600 feet. So 1 mile and 2/10 of a mile. Just to summarize what is provided, and then we'll go look at some of the data. Cross section White Oak upstream has its low elevation of minus 4.3 feet. It's 6,600 feet long, and the change in elevation is 2.41 feet per 6,600 feet for a bottom slope of 0.3%. Buffalo Bayou on the upstream side is going from minus 11 feet to minus 9 feet for a change in elevation of minus 2.2 feet. So that's an adverse slope, at least for nearly a mile, of minus 0.054%. And Buffalo Bayou moving downstream is has a low elevation of minus 16 feet, which is determined from the cross section, 4,000 feet away from the confluence, for a net change in elevation of 1.86 feet, which leads to a bottom slope of 0.4%. So it's, again, just a fairly interesting confluence. And the other thing interesting about this case study is, unlike many of the case studies that we do in engineering classes, not real life, but classes, we have elevations that are expressed as negative numbers relative to some elevation data. And so we have to be fairly precise in our handwritten work to be sure we're capturing that we're going from a large negative number to a smaller negative number, and so on. We're going to be provided with rating curves for the cross sections. And what we want to do is, using the supplied hydrograph, simulate the behavior of the confluence, either in steady conditions or dynamic conditions, and then produce a plot of the water depth in the confluence under these two conditions. And the goal for that in the original study, and I'll get to that in a second, was the peak flows in steady flow. When they combine here, the water in the confluence is too deep for building jails and stuff like that. But because the peaks tend to arrive at different times, use of the dynamic model was able to demonstrate that it was likely that the predicted inundation wouldn't happen. And it worked great until Tropical Storm Allison came along, and then Hurricane Harvey, and then whatever the next thing that's going to come along. So best is to get the models built, sold, and get out of the area quickly before the weather changes. I'm just kidding. I mean, it's true that these flooded on at least 3 occasions after this model was built. My name's on the model. But those were rather extreme flooding events, and they haven't come back to hunt me down and kill me. I'm thankful for that. Okay, let's look at the White Oak upstream cross-section data. So here is what White Oak Bayou, it's labeled cross-section 4 at the I-45 North ramp. And the leftmost column is the stationing relative to some XY data. And then the next column is the elevation of the bottom of the channel at that point, and then where applicable, Manning's End is supplies. So moving from station 4247 to station 4949, the land surface elevation changes from 50 feet down to just a bit under 11 feet. And then at that location, there's now a change in Manning's End. So we're now entering what would be considered the channel part of the cross section. And that goes from 4960 feet all the way to 5043 feet, where again, there's now another change in Manning's End. Let's examine between that station and that station. We see at 4960 feet when we enter what's treated as the channelized part of the cross section. Our elevation goes from 10 feet to 9 to a little bit below 0, down to a -4 feet, and then starts coming back up, -3 feet, -1 foot, 0, 2 feet, 8, and almost back to 11. And then there's an abrupt change in Manning's End. It goes from 0.015 up to 0.5. Now 0.5 is a fairly large value of Manning's End. That's something that would be appropriate if there's a lot of trees, or in this case, buildings or structure in the way that makes the cross section, at least in a one-dimensional flow construct, quite rough. 0.015 is the other extreme. That's actually a fairly small value of Manning's End associated with relatively smooth materials. In this case, that happens to be a concrete line channel in that region. And then moving from station 5000 up to 5582, we get another large change in Manning's End and a very unusual value. So a value of 0.99 is quite unusual, and whoever made this cross section is attempting to convey to a computer program that I want you to treat that as very high resistance flow indeed. And then on out to 6521. So unlike what I've presented so far, the stationing is in some sense arbitrary because we don't actually know where the reference position is. But we can always find we are able to find the lowest value in the transect and declare that that's going to be along the thou egg of our model. So that's White Oak. If we look at the equivalent Buffalo Bayou upstream cross section, the numbers are different, but the same pattern is displayed. We start at station 3602. with a relatively high Manning's N. We get to station 4879. There's a change in Manning's N as we're entering a channelized type situation. And then we get to what is likely the true channel at 4934. You notice that the roughness coefficient of Buffalo Bayou in this regime is nearly 3 times bigger than the White Oak Bayou one. Now, why might that be so? You might be asking yourself. And the answer is that compared to White Oak Bayou, Buffalo Bayou is relatively natural channel lining. Trees and dirt, crawfish, alligators, shopping carts with only 3 wheels. I was going to go bum encampments, but that's just mean. It's not concrete lined, I guess is my point. And so now we're moving down to a land surface elevation of minus 11.52 feet, and that coincidentally occurs almost 5,000 feet from the reference stationing position, just like it did in White Oak. So with a little effort, if it was necessary, these stationing numbers could be re-indexed. What I no longer have information on is what the orientation of the cross sections is relative to the channel Thoweg. I know that Thoweg is 5,000 feet from somewhere, but I actually don't know quite what direction that is. And I'm a bit on the, I would say, too lazy side to go find out, but I'm pretty sure I have lost the data forever. But what we have here is sufficient for today's discussion. And then as we leave the Thoweg, we start to get smaller and smaller negative numbers, hit 0. We get positive elevations. At 5106 feet, our Manning's N changes from 0.04 to 0.07. So while we're still, that's a fairly large value. And we move all the way on out to where 5,000 feet from the station datum. And we'll take one more cross-section look. We'll look at the Buffalo Bayou downstream cross-section. And again, we see the same pattern repeated. We have Manning's N of 0.15, elevation of 42. As we move towards the center line of the channel, our Manning's N is now reduced to 0.035, grassline channel. The Thoweg's at almost 5,000 feet. And as we come back up the other side of the channel, Manning's N abruptly changes to 0.2 to reflect the buildings and trees and physical structure that would be in the way of flow in that cross-sectional area. So that's the information we have on the 3 cross sections. We also know to some extent what the slopes are from those reference cross sections to the confluence, and we can use that information to replicate these cross sections in a computer model by simply offsetting these depth values based on the slope and the position of the intermediate cross section relative to the confluence. The other information that we have are rating curves, and the Buffalo Bayou rating curve looks like this, and I will explain the pertinent parts. So this junk up at the top looks like Perl script on how to render this rating curve to a website, which is where I actually obtain the data. And then the standard government warning. This rating curve should not be dependent on anything that can get the United States of America sued. As such, we disavow any knowledge of its existence should something bad happen to you. That's just translation. I'm being kind of cynical at this point. But they rarely commit to anything. So you always see this word provisional, and you, the end user, are responsible to use the information wisely. And then it has some more information on the rating curve. And then the last part is what's interesting. Let's see if I remember how to read these, because it's been a while. Okay, the locations that have an asterisk represent a point on the curve where there's an actual data point. Where there's no asterisk, that's intermediate interpolated values. At a depth of 1.6, let me see if these are depths or if these are actually stages. Okay, so the leftmost column is gauge height in feet. So those are stages above the reference sea level. The next parameter is the discharge in cubic feet per second. And dependent storage, depth routing. Rounding. And I can't quite remember what this last element is, but I do know the asterisks represent actual data. So as if the water in this particular river is 1.6 feet deep gauge height, there's no meaningful flow rate. The water is stagnant. And it shouldn't have this many zeros. Well, that's not a very interesting rating curve. I think I've missed a column. Independent, shift, depth store. It's gotta be gauge height. Oh, there's no shift to the gauge. So it's the last column is discharge in cubic feet per second. So if the water is 1.6, if the stage height's 1.6 feet, there's a measured value of 144 cubic feet per second, which is not too shabby, but these are big bayous. At 2.5 feet, there's a measured rating of 363 cubic feet per second. At 3 feet, 509. And as we continue to increase gauge height, you can see the numbers growing. And let's go all the way down to the bottom. So when the water surface elevation in Buffalo Bayou is at 37.5 feet. And if you remember what the bottom of the bayou was like -14, so that's a flow depth of 47 and 4, like 51 feet of water. We're at 16,000 cubic feet per second. So this relationship is called a rating curve. And what it allows is, if we know the water surface at some point, we can stipulate a discharge. Similarly, if we know the discharge, then the rating curve suggests to us what the proper water surface should be. So that's a Buffalo Bayou rating curve, and then we have a similar rating curve for White Oak. Let's take a look at White Oak, the smaller bayou. At a gauge height 5 feet, we have about 1 cubic feet per second. And if we get the gauge height, I don't think it goes up to 30. Could be wrong. Gonna be wrong. Gauge height of 43 feet. We have 28,000 cubic feet per second running down the stream. And if you look at these latter numbers, you'll see that it's apparent to me that these are an extrapolation. It's very insensitive to a tenth of a foot difference in stage. So those are two rating curves that we have, and those are important for establishing either boundary conditions or input conditions to a model. You notice we haven't run anything modeling yet. Oh, okay. My bad. So we looked at the rating curve. We looked at downstream cross-section. Looked at the white oak rating curve, upstream. The other thing we have are some input hydrographs. I'm not sure what happens, so I click on an Excel file. It's going to ask me to open it, see if we can do this. Of course not. That's better. So what we're given is we're going to be given an upstream hydrograph. Look in hours, and we can see the relationship of time and discharge as an input boundary condition. So go ahead and just plot it real quick so we can get a perspective of what that hydrograph looks like. So there's our input hydrograph, not very much happening, and then about hour 10, it rockets up here to 12,000 cubic feet per second, and then starts its descending limb. And we'll look at a white oak input hydrograph. We'll take a look at its behavior. It didn't work. And this one, boring, and then it starts to rocket up here. And I don't know if I made a mistake here, but it either has this flat connection and then comes back down. Let's go see what's going on there. That is at 0.18.5. If you look at the difference in time, there's a pretty big gap in time. So there's some missing data in here. And sometimes we have to just accept that. Okay, so we have an input hydrograph on Buffalo. We have an input hydrograph on Whiteout. If we return to our drawing, that input hydrograph, I'm getting feedback now. That's weird. That input hydrograph uh, would be on the upstream end, same for the input on Buffalo. And now where the rating curve comes in handy is we can apply that on the downstream end, which gives us the pieces that we would need to run a simulation model and examine the behavior of water in Allen's Landing and determine whether or not the vicious seatbelt violators that are held on the bottom floor of the jail have to learn how to breathe water or not when it's flooding. So let's ask ourselves, suppose we had, if you're interested in the background of where this problem comes from, I left a copy of a paper that is used to motivate this modeling problem. And here was the information that was available at the time. Here is some bathymetry data. These were the cross sections that were provided to the modelers. There's the old spaghetti warehouse. I was slightly to the wrong place in the new county jail. And then these were the existing cross sections. And there was going to be a change on some of the cross sections in White Oak. So that was literally all that was going on. And then as good authors of papers do, you attempt to use every letter of the Greek alphabet and a few that haven't been invented yet. And I'll let you read that on your own later. At the time, we were doing a three-dimensional model, and so the computational grid is a little bit complex compared to what most of us are accustomed to. And this predates a lot of the graphical user interfaces that are available nowadays. So this grid had to be hand built. And the key thing is that in order to start the multidimensional model, we had to have hydrograph behavior and actually had to run a one-dimensional model to seed things. And so this is quite relevant. Here's the two hydrographs that we're going to examine. And so I can actually get that missing peak from here if I need to. It occurs at a little around hour 20, and if I remember, the missing peak was between hour 18 and hour 30. The remainder of this paper shows the velocity vectors that were computed and so forth. So that's the background for this particular problem. So now let's ask ourselves, if we were to model it, what would we have to do? Well, if our tool is swim, first we're going to have to build a layout for the model. We'll have to identify what Buffalo Bayou is, what White Oak Bayou is, and how they're interconnected. We would do that by starting up swim, which we'll do in a little bit. Drat, I thought I actually had swim files. I don't want to build that with you guys watching. We would start up swim, and the first thing we do is lay out nodes. Then we join the nodes with links. And then for each of those links, we would apply those cross-section informations adjusted for different elevations to preserve the channel slope on White Oak Bayou to the confluence, upstream Buffalo to the confluence, and then Buffalo downstream. At the downstream most end, we have to decide on what's an appropriate boundary condition. Eventually, we'll have to pick one, but it's possible to use the rating curve to approximate the downstream boundary condition. The upstream boundary conditions would be the input hydrographs, and then we would run our simulation. Now let's see if I happen to have the swim models already built. Reading source, latex source. I do not see an input file. I know I've done this in Swim already, so well, let's get Swim up and running, and then we'll go find the files. I'm not going to bore you with watching me input transect information, but we can at least get our Swim model started and add any additional files to the mix. So we'll run it on Amazon Light Sail, because at the very worst, that at least creates a copy that I can share with you. This is new behavior for Amazon. It's kind of annoying me. Trying to be sure I'm not a computer. You'd think they could look through the camera and tell. Because I bet if I took my wallet out and held a credit card here in the camera, they'd be able to charge it no problem. Okay, so all I'm doing right now is firing up my my Windows operating system instance on my remote computer. And I'm really only doing this because my desktop computer is a Macintosh, and Swim doesn't play well on a Macintosh. I can make it work, but it's just not ideal. So there's my problem from last time. Let's go ahead and save everything. Exit. And I'll restart Swim. I know that seems dumb, but on a virtual machine, you get to do that a lot. And I'm going to my remote browser so I can access whatever data files I have here. And I hope that I have hopefully I left a BMP file. I did not. Let's go ahead and first get a graphic file so we can at least do a backdrop. We need BMP. Can't believe I didn't leave the files around. I'm not normally that stupid, so I'm sort of frustrated with myself. Nothing. Not here. See if it's here. While that's loading up in the background, let's go back here. Refresh this guy. And if we were building from scratch, we could first load a backdrop image. And there is our backdrop image that we could work on. We would have to decide what kind of nodes to use. Actually, we'll start everything as a junction node. Downstream is over here on the right. Upstream is here on the left or here at the top. And so we could make our downstream-most node right there. That represents whatever the outfall condition is. And a couple of nodes to represent our system as we move up into the confluence. And just follow the positioning of Buffalo Bayou. I've put in more nodes than we might need, and now we'll go ahead and work our way up White Oak Bayou. White Oak Bayou actually goes under the interstate. We might do something like that. The next thing I would do, I have the advantage of having done the problem before. That one I'm going to convert to a storage unit to keep, because we have dimensions of the confluence. Then I would go ahead and start building my flow model. And because my clients would be extremely disturbed by straight lines cutting across the street, I'll take advantage of the graphical user's interface tool's ability to draw renderings of curved things. As far as the computer is concerned, the hydraulic algorithm has no knowledge of that curvature. In fact, it can't even use it. But the human being observing it or having the information explained is comforted by drawings that look like that. That's a aspect of engineering known as client management. It's not deceitful, and what I just told you is what I would do in a public hearing if I was demonstrating it. You know, I would say that even though these links are visually following the Bayou internally to the computer, they're just direct connections, and we, the analysts, have to provide the necessary correct distance information. And lastly, White Oak. So there might be our initial rendering, and a lot of times what I'll do is I will turn off the backdrop and go, okay, yeah, that looks like what I want it to be. As of this point, we could run the thing and there's no information. It's just going to sit there and not know what the hell is going on. Oh, okay, I was just able to put zero flow through my system. Big deal. I knew it. I knew that ahead of time. So that would be our first step, is laying out the broad overview of the model. The next thing we would need to do would be to change that conduit from a circular one to something that makes a whole lot more sense for this problem. And the information we would use to do that are those transect files. Now bear with me while I see if I can find the copy already built. you guys who use Windows all the time, does it do this crap to you too?
It does that every time. Every time you need it, it asks to be restarted.
God.
That's pretty normal.
Thank you for confirming my deepest fears on that. Yeah, Windows has detected you move your mouse. Would you like to upgrade the operating system? That kind of stuff. Okay, so let's see how I would find it. Oh, please, please. "2015, I don't think that's mine. No. Okay, this is the one we've already done ourselves. Okay, those elevations are not Houston. All right, where else would I have hidden it from myself? Hopefully I ran it in the last couple years and it's still in the swim directory. Oh, Confluence Houston. Okay, everybody, this is, I'm gonna need everybody's help here, so cross your fingers and toes. Thank heavens. You do not know the sense of relief I have with that particular drawing. Okay, so it looks like I have an input file, and let me see if I can find the path to it. EPA Swim Project Confluence Houston. Minimize that. There is something here called EPA Swim Projects. There. Thank you. Okay, example one in Confluence Houston. Okay, let me see if I can get that thing uploaded to the server so that we all have access to it. Here's me presuming that you guys actually want access to it, and just hoping for this to become a bad memory someday. Okay, so there's the server. Here's the file, I think. Okay, let me bring it to the desktop. See what this example one is before I commit. And that does not look like this problem, so I'm not going to worry about it. We have the Confluence file, so let's go ahead and move it onto the server. I don't want to go to Blackboard. I want to move to the server. Okay. Did I lose my anaconda? Where'd it go? All right, so there's our swim model I was messing with. I'm going to go ahead and wipe this, and we'll so I'm just saving it in case I have a need for it in the future. Now we will open Confluence Houston. I'll turn off the backdrop temporarily. So there's the Houston model that we're going to examine. So this has far fewer nodes than I originally drew. And if you had better cross-section information, you certainly could leverage that and add more nodes as appropriate. Let's go just take a look at Conduit 6, which is an irregular node. Water is allowed to reach a maximum depth of 65.04 feet above the bottom of the cross section. There's a net roughness of 0.035. Well, when we look at the section, we might see that we're having spatially varying roughness. And that link is 2,500 feet long. So we are representing from storage unit 3 to junction number 2 is 2,500 feet. And then I presume from junction 2 to the outfall is another 2,500 feet. But if we look at this, is identical from the preparatory material that I demonstrated. So here we're moving from the left, we have these different elevations that are taken from the input file, and we're dropping down into the Bayou, and then we come back up the other side. And at this uppermost elevation, we're out of data. Because we set a total depth of 65 feet, we have the equivalent of vertical walls at each end. So should the water get, in this case, deeper than 42 feet, in reality, it would be expected to spread to the left of the diagram. In our computer program, we've artificially restricted the ability for it to spread, which we as modelers would have to be aware of. If we started getting results that the state of the water surface was maybe at 48 feet, when we look at these sections, we'd realize, well, if it's 48 feet, it's trying to spread to the left. We've either made a big mistake somewhere else, or the cross section needs to be relaxed and extended. And here is the input table, and that is clearly a cut and paste from the Buffalo Bayou downstream .txt file. If we look at white oak, we'll look at the same information for white oak, but it'll have different numerical values. So there's the white oak one. And the important part in all of these is the lowest elevation. Let me see if I can find it for white oak. So minus 4.3 is our low elevation on that. Transect. We go to the next conduit. In order to preserve downhill slope, we don't expect the lowest to be at minus 4.3 unless I've made a big mistake, which should be around 5,000. Oh, these don't have slope yet, so that's also showing at minus 4.3. So this is an incomplete model because the modeler, me, has not adjusted for the bottom slope changing. Let's see if the junctions are at different elevations. So that is at elevation 81 feet. That one's at 62 feet, so it is moving downhill. That one's at 43 feet. That one's at 25 feet, 12 feet, 0 feet, 37 feet, and this should be bigger than 37, 50 feet. So it does look like the junctions are preserving the correct elevation. Let's take a look at a profile. Keep in mind we haven't actually run the simulation yet. We're studying basically the equivalent of our input file. So there is our White Oak Bayou coming into the last two is Buffalo Bayou. It's barely discernible in this graphic, but there is a slope change between the two. And then we have these upper limits to flow. And you notice this funny looking one happens to be the confluence, because what we can't depict is there's actually another channel connecting into this. We'll look at the other one. We'll actually go all the way to the outfall. So this is the Buffalo Bayou main stem. And I'm actually setting up for the actual simulation. So even though it seems like I'm doing this stuff willy-nilly, I actually have a plan. Dang it. I hate it when it does that. Okay, so here's my visualization plan. The upper profile is White Oak Bayou to Buffalo. The lower profile is Buffalo entirely. This section, these two links right here, and these two links right here represent identical location. They're the same as each other. And unfortunately, the free interface swim program that we have access to can't render the two profiles on the same drawing. There are commercial products such as XP Swim, which can render those two profiles on the same drawing. And in all likelihood, if you're doing this at a firm, they probably have paid for those value-added features. But the computation engine underneath is the same. So we're not getting cheated using the free one, except when it comes to making pretty pictures. Let's look at the input boundary condition here. Oh, this is currently set up for a steady flow case. So the White Oak input is 12,000 cubic feet per second. Actually, that worked out pretty good. I haven't put in the hydrographs yet. Cool. And then this one is set for 1200. That seems wrong. And our outflow boundary condition, I bet it's a free outfall. Oh, fixed stage at 9 feet. And let's see, 9 feet should be 1200 plus 12,000, which should be 13,200. And if we take a look at the Buffalo rating curve, 9 feet should correspond to around 13,000 CFS. Let's hope I am interpreting this right. Not quite. If we have 12,000 plus 1,200, we should be somewhere up here between 31 and a half feet. So I may, again, still have a mistake. It's definitely 9. I think that should be 31. Let me check this one again. It is 12,000. Well, let's run it this way with a 9-foot outfall, which should be very convenient for the model. And then we'll go ahead and put the correct downstream boundary condition. Oh, that was amazingly quick. So here is our simulation. And it's telling us that this is what we would expect in those conditions, but that 9-foot fixed depth is far too favorable. Let's go back and put what the number should be. So this should be, if we're going to use a fixed outfall and a steady state, this 31.5 was what was shown there. This system is quite comfortable with those flows. Our next step will be to place those two input hydrographs. Let me save everything. But that doesn't save it back to the server. Okay, that's fine. So now we have a model set up that we're going to explore next time. What we'll do next time is we'll put in the two hydrographs and we'll see what the behavior in the Confluence is. The other thing in the Confluence is I used a storage curve to represent the depth in storage in the Confluence itself. And of some importance, the invert elevation is 25 feet above sea level. And then let's see, this one is 43 feet, and this is probably going to be similar, 37 feet. So there's a good 12-foot drop over 2,000 feet to get into the confluence. Oh, wow, time went by quick, at least for me. So we will pick up this case study next time and we'll complete it. So what we'll complete it with is we'll run the, we'll put in the two time-dependent hydrographs and take a look at what the outfall boundary condition should be. And then that will conclude our confluence or tributary type case. And then where we'll head to next is we'll look at a case study that's very similar to this one, only it's the entire drainage network of Harris County, which is certainly going to be more complicated than one main channel and one tributary. And that's where we start getting the power of our modeling features. So what we have drawn right here, we could conceivably do that in our own Python scripts, although we would probably immediately conclude that's stupid. If you make me do it, I'm gonna go find another job. When we get to more complicated cases, we have to use software tools like this. And so I'll just demonstrate one and make the files available to you. Like this one, it is currently incomplete, but you'll get an idea of the level of complexity that we can do. So in review, before I call it a night, I think what we've done, we started with a single rectangular channel in steady flow. We added the necessary computational capability to handle unsteady flow. We changed the geometry from a rectangle to, in this case, any geometry that we can conceivably represent in tabular form. Then we went from it being a single channel to having a drainage conduit with lateral attachments at different points, which is what this drawing is. And now we're going to go from that to many of those to examine a total drainage network. And that will pretty much beat to death about the level of complexity that we can get with branched one-dimensional networks. The next step beyond that will be to start essentially creating a loop. I mean, mathematically, that's what we do. But for a particular node, it'll have more than two directions flow can go. It'll have more directions, and that way we can start to incorporate what I call a quasi two-dimensional representation. It's not true two-dimensional as the fluid mechanics people would do it, because we don't have the momentum transfer from the cross term, because we have no way to represent that using a network model. But it's close enough for many engineering practical cases that we might want to study. All right, well, that seems like a good stopping point for right now. So I want to wish you all a good evening and take care. And I haven't looked to see if the other assignment, I don't know if it's due today or this week or not. But if it is, I'll bring it up next time so that we can all be confident that we're making good progress on it. And we'll take it from there. And again, have a good evening and thank you for your patience and attention. For the three of you that are in Lubbock, I hope you get a good night's sleep and this dust and cold wind doesn't wreak too much havoc on your throat and sinuses. And for Jawad, I want to wish you a great day today since it's morning time for you. And I hope you have a wonderful day. And we will pick this up again on Wednesday.
Thank you, Dr. Cleveland.
So good night, everybody.
Good night,
Good
Dr.
night.
Cleveland.